Hi, go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. Okay, this video isn't quite what it says on the tin because in this problem we don't need parallelograms, as all the vectors are pointing the same way, vertically down. In the first part of the story, a stone falls freely through the air, and in the second part it falls less freely through the water, but straight down to the bottom of the lake. But you might like to know that you can tackle an awful lot of these so-called SUVAT problems, which is to say the ones involving constant acceleration, with a diagram, specifically with a velocity time graph. Just labelling a graph like this in a sensible way, providing labels wherever we can for important features, and then seeing how to work out the remaining labels from there can be easier than fretting over a list of formulae. Okay, I have to backtrack slightly here. If time isn't involved at all in the problem, if we don't know the time taken and we don't have to find it out, then be ready to use, specifically v squared equals u squared plus 2as, that one. And a graph might be overkill in those cases. But if time is involved, it's the other way round, and the graph is usually simpler, even for the part where you could have used v squared equals. And this way, the graph way, can help you to engage with the problem and understand what's going on, whether or not you feel reassured by filling in a formula as well. Which you certainly don't have to, by the way. An examiner will be just as happy with a properly labelled sketch of the graph, and probably even happier. So in this case here, since time is involved at some point, let's use a graph. And so, our velocity time graph starts from the origin, as the stone is released from rest, meaning a zero velocity, and then it shows the velocity increasing at a rate which we know is constant, hence the straight line with a constant gradient, which, as usual, we assume is 9.8 for free fall under gravity. But then we can also see that the gradient must be the result of 14, the velocity increase, divided by t, the time taken. That's going to be the rate of increase in velocity. 14 over t. So we know 9.8 equals 14 over t. So they are both equally good expressions for the gradient. So we know t is 14 over 9.8, which is 14 over 49 fifths, or 14 times 5/49ths, or 10 over 7. So now we can give them the time. And then we very quickly know the distance on the principle that the area under a velocity time graph always gives us just that. And by the way, this principle is obvious enough in any of the cases where velocity is constant. In those cases, the area under the graph is just a rectangle, and calculating that area pretty obviously corresponds to multiplying speed by time, which we know must result in the distance covered. And then if the velocity changes at a constant rate, as we are always assuming in SUVAT problems, then it's clear enough how the principle generalises. Although, of course, it generalises even further, quite apart from constant acceleration, and we'll make use of that in question 7. Anyway, here we can see the distance travelled in this first episode of question 1 is going to be the time taken times the average speed, which we can see is 7. So whether we think about the triangle or the rectangle, which is half as high, we have the time times 7. So the 7's cancel and the distance is 10. And then the second episode is not very different. It's just that the velocity, increasing as it does from 14 to 20, creates a trapezium and not a triangle. This time we are told the area under the graph. It's 15. But then we know that this area is also going to be the time taken, whatever that is, we're calling it t, times 17, which is the average speed. Or, thinking about the geometry, it's the mean average of the two bases of the trapezium. These two bases are vertical, but let's call them bases to remind us that the area of a trapezium always is the mean average of the two bases times the height. In this case, a vertical height. So now we can elaborate our label for the area to say that yes, it's 15, but also it's 17 times t. And because of that, now we can see that t is equal to 15 over 17. And then the acceleration, which is what they want, is the velocity increase of 6 divided by the time taken for that increase. So 6 over 15 seventeenths, or 6 times 17 fifteenths, which is going to cancel down to 2 fifths of 17, or 4 tenths of 17, or a tenth of 68. And we're done.